very quickly. And you've covered most of it in O-levels physics. So ideal gases. I mean, the topic name in the syllabus is states of matter.
Sir, is this a new topic?
Yes.
Okay.
Okay, I'm going to share the question videos playlist for energetics. Okay. So now ideal gases. It's simply most of the stuff you've studied in O-levels chemistry, O-levels physics, which is that you have a container and that container has gas particles in it. So what would the container look like? It's going to have these particles randomly distributed far away from each other. So that is what gas particles look like, and they're haphazardly or randomly moving around in all directions randomly. So they're all moving haphazardly and randomly in all directions. So the first thing is we're going to study what did you study in O-levels about a gas? What is gas behavior? So you had you talked about all sorts of things. You talked about I mean, what is the arrangement? It's an irregular arrangement. One second. So it's an irregular arrangement. How are the particles arranged? They're far apart from each other. That's the second point. So particles are far apart in gases. How are the particles moving? They move freely and randomly in all directions. So they're going to move freely and randomly in all directions. Acha, what else did you study in O-levels about gases? They have weak intermolecular forces, so they don't really attract each other. That weak intermolecular forces, so they don't really attract each other with a strong force. So we studied all of these things when we talked about gases. So this is what a gas looks like. So the thing is, okay, when you talk about ideal gases, you're basically trying to create a model of a gas, and you're trying to derive certain formulas by looking at how the gas would behave. And I mean, your assumption is that you're going to apply those formulas that you derived on a real gas, on an actual gas. So an ideal gas is just a model of a gas. Now, when you talk about an ideal gas, there are two main assumptions that you make when you talk about a gas. The first, so I mean, remember in your exams, they'll frequently be asking about these two assumptions. So there are two main assumptions. And those two main assumptions are, so let's talk about those two main assumptions. The first one is, we already talked about this, that they have negligible intermolecular forces. So that's your first main assumption. Now, this assumption is true under certain conditions. Gases always have negligible intermolecular forces, but they will always have intermolecular forces when the particles are really energetic at high temperatures. So if this particle is energetic, it's got very high energy, then it wouldn't really care about the force of attraction. For example, if you have a carbon dioxide molecule and you have another carbon dioxide molecule, the molecules might be attracting each other very slightly, but at high energy, they can easily break the intermolecular forces. Water is a gas at high temperatures. Why is water molecules gaseous? Because water molecules are so energetic that they don't really care whether they're attracting each other or not. They've got so much energy that they would easily overcome those intermolecular forces. So gases have negligible intermolecular forces, but this statement is going to be truer at higher or more true at higher temperatures. So imagine if you have steam and you start lowering the temperature, it would stop behaving as a gas. It would liquefy, it would condense, the intermolecular forces would become relatively stronger. The particles would not have enough energy to break those intermolecular forces. So remember this, negligible intermolecular forces, gases do have negligible intermolecular forces, but this point is true at high temperatures. They've got more kinetic energy. And they easily break those intermolecular forces at high temperatures. At higher temperatures. Okay, is this point clear? The first one, they're going to ask you about this frequently. Okay, so is this clear? Mahad, Raid, is this clear? Yes or no? Also, is this clear? So now the second point, which they're going to ask you, the two main assumptions. The second point is that the volume of the gas particles is negligible. Is negligible compared to the total volume that is occupied by the gas. Occupied by gas. Now, this particular point is phrased somewhat differently at times. They also state that that the atomic radius or the radii of the particles is negligible compared to the intermolecular distances. Compared to intermolecular distances. Now, both points actually mean the same thing. What both points are referring to is you have this container. Most of the container is just empty spaces. Like if you look at most of the container, it's just empty spaces. There's nothing there. I mean, you've got all these gaps. There's nothing there. So when you talk about the volume of a gas or the total volume of a gas, this is the total volume of a gas. The container. So that's the total volume of a gas. But it's mostly empty spaces. Like if I were to pick all these molecules and I were to bring them together, then the particles themselves are not really occupying much of a volume. Like if I bring all the particles together, I mean, their volume would be kind of negligible. They would have a very tiny volume. So the volume of the gas particles is negligible because when you talk about a gas, or when you think of a gas, gases are mostly just empty spaces. They're particles flowing around and the distances between the particles are large. The particles themselves are very tiny. but the distances between the particles are really large. So the second statement meant that the radii of the particles is negligible compared to the intermolecular distances, or what you can say that the volume of the gas particles is negligible. So all you see is mostly empty space. The particles themselves don't have much of a volume. So these are your two statements. Now, this particular statement, the second one, is going to be true at low pressures. It's going to be true at low pressures, and the reason is so I'm going to explain or draw two diagrams. One is a gas being at low pressure, and one of them is a gas being at high pressures. So the second statement basically means there's a lot of empty spaces when you talk about a gas. So let's say you have a container and it's got a movable piston. So here's a movable piston, and this container has some gas particles in it. And then, so that's at low pressure. So if I were to increase pressure, what's going to happen is I'm going to press down on the piston. So if I were to increase pressure, so here's the same container, and now it's going to be at high pressure. At high pressure, the gas will compress. It will start compressing. So here's the same gas at very high pressure. So over here, I mean, what the second statement basically means is, in simple words, it means that gases is mostly empty spaces. So you've got a lot of empty space over here. So the volume of the gas is basically just the volume of the empty space. The gas particles themselves have negligible volume. But when you're at high pressure, the empty spaces they go away because you're compressing it. So all the empty spaces are gone. So the volume now of the gas particles is no longer negligible because it's almost the same as the volume that's occupied by the gas itself. So this statement basically means that when you think of the volume of a gas, it's mostly the volume of the empty spaces. So it's mostly the volume of the empty space plus the volume of the particles. And we say that this is almost negligible. Most of it is just empty space. The volume of the particles is like, the particles are really tiny, so the particles themselves are not contributing much volume to it. So it's just these empty spaces plus the volume of the particles. But when you take the gas at a high pressure, now the volume of the particles is no longer negligible because now what's happening is that the total volume of the gas is the volume of the empty space. Now the volume of the empty space is a lot lesser because you've compressed it. So the volume of the particles it's no longer negligible. It's no longer smaller. They're both almost the same. So it's no longer negligible. So I'm going to sum this up. I'm going to sum this point up. Okay, what the second point meant was, okay, gases are mostly empty spaces, which is true at low pressures. Because at low pressure, gas is mostly just empty space, but it's not true at high pressures. When you compress a gas, the particles are all tightly packed now because you've taken out all the empty spaces out. So so now there are no longer empty spaces in the gas. It doesn't look like a gas at high pressures. So the point I'm trying to make is that the first thing is a gas is going to behave as a gas at high temperatures. That's the first thing. Or it's more likely to behave as a gas at high temperatures, which is pretty obvious because at high temperatures, the intermolecular forces can be easily broken down. And the second point is that a gas would most likely behave as a gas at low pressures. Why? Because at low pressures, the particles would be very far apart. There would be problems that would happen. So low pressure, a gas is more likely to behave as a gas. The problem is that at high pressures, particles are so close together particles are very close. And because of the closeness, the intermolecular forces become stronger. So when you take a gas at to a very high pressure, what happens is that the particles are so close together that even if the intermolecular forces is weak, remember a force is always inversely proportional to distance. Like the closer to the, if you have two magnets and they're very close together, there's going to be more force. If the magnets are very far away, the force diminishes. So the same thing happens over here. Even though the intermolecular forces are weak between them, but if you bring the particles really close together, the force of attraction would become strong and it would either liquefy or solidify. It would stop behaving as a gas. The particles would stop moving randomly and freely in all directions and it would stop behaving as a gas. So particles are very close together. And if they're very close, intermolecular forces relatively become very strong because of the closeness. And gas would most likely liquefy or solidify. At high pressures. So these are your two main assumptions when you talk about ideal gases. You can remember that. And remember to quote this, you get a lot of questions on this. And always remember that any gas would behave as an ideal gas or a model of a gas, or any substance would behave as a gas. Whether it's liquid, water, it's going to behave as a gas at high temperatures and low pressures. Not high pressures, high temperatures and low pressures. So water is going to probably behave as a gas at high temperatures and low pressure, which is pretty obvious. So is this point clear? These two main assumptions. Yes or no? Is this clear? So is this clear?
Yes.
So the next thing we're going to deal with is the other formulas. So you deal with these two assumptions. The next thing we're going to talk about is the relationship between, or we're going to construct the ideal gas equation. The first thing is pressure is directly proportional to temperature. That's the first relationship. You've studied that in O levels as well. So pressure is directly proportional to temperature. And the reason is, if you have a gas, you take it to a higher pressure, it's going to collide with the walls of the container with more force. So the explanation for that would be that particles are more energetic. Or they are more kinetic energy. And you get more frequent and effective collisions with the walls of the container. Frequent and forceful collisions at high temperatures. So jitna zyada temperature hoga, high temperature, that you're going to get more frequent and forceful collisions. Hence, there's going to be more pressure. And when we talk about a relationship between two variables, we're assuming, remember, we're always assuming all the other things are constant. So pressure is only directly proportional to temperature if everything else is constant. Remember, whenever you study relationships, all else has to be kept constant. Only then would the relationship make sense. Similarly, you have another one, which is that pressure is inversely proportional to volume. So it's inversely proportional to volume. We just did this over here as well, that whenever you increase pressure, so whenever you're going to increase, I'm just going to copy this. So whenever you're going to increase pressure, the empty spaces between the particles would disappear and the volume would start decreasing. So whenever you try to increase pressure, the volume is going to volume would proportionally, it's inversely proportional, so it's going to decrease. That's the second one. And then there's a third one, which is that pressure is directly proportional to the number of moles of the gas. So that's the third relationship, and N is number of moles. Now this obviously makes sense. You have more particles, there's going to be more pressure. So you've got a gas, you got more particles, you're going to have more collisions. You add more particles to it, you increase the number of moles somehow, and there's going to be more pressure exerted. So that also obviously makes sense. Ye तीनों bhi clear hai? Is this clear? Also, is this clear, Mahad? Raid, Sidra, is this clear?
Yes, sir.
So you've got these three relationships. You've studied this in O levels. We're going to even make the graphs. They ask you for the graphs for this as well. So pressure and temperature are directly proportional. So that's obviously a constant straight line. When the temperature is 0, actually, also the last one was you have more gas. This is moles. Pressure is directly proportional to moles. You have more gas, there's going to be more pressure. You'll have more collisions with the walls of the container. You have less gas moles, there's going to be lesser pressure. Is this clear? अच्छा अब ये graphs कर लेते हैं. We've got this is the graph of pressure versus temperature. Okay, that's one of the graphs. Then you have the next one, which is pressure is inversely proportional to volume. So remember, what is the graph when you have an inverse relationship? So that's going to be, it's going to look like this. So it's going to look like this. This is an inverse relationship. And pressure is directly proportional to the number of moles. So that's also going to be a rising straight line. You have 0 moles, there's no pressure. So it's going to pass through the origin. So those are all your relationships. Now, what I'm going to do is I'm going to combine the three formulas together. And I'm going to make one simple equation. So pressure is directly proportional to temperature. It's inversely proportional to volume and directly proportional to the number of moles of the gas. So I'm going to combine all the three variables into one relationship, which is, we've got pressure. It's directly proportional to the number of moles and the temperature. And it's inversely proportional to the volume V. So we've got this relationship. And I can convert this relationship and rearrange this and write it like this. I can take the V to the other side. So it's going to become PV is proportional to NT. And now to get rid of the proportionality, what I need to add is I need to add a constant, which would be known as the gas constant. So the formula would now become PV is equal to N T, and there's going to be a gas constant, which is known as R. So to get rid of the proportionality, I've introduced this constant, which is R, and this R has a value. This is known as your ideal gas constant. and it has a value which is 8.31. That's going to be our constant. So again, I'll just quickly go through this. Pressure was directly proportional to moles. It was directly proportional to temperature, inversely proportional to volume. So I just rearranged that. And to get rid of the proportionality, what I did was I introduced R as the gas constant. And I got this equation over here. Ye bhi clear, Sanoko? Is this clear? Hania, Izhan, is this clear, Aisha? Amna, is this clear? Is that clear? So now the only thing that has to be done about this is yes, 8.31 is the value of the gas constant. You have to remember this. I mean, you don't have to remember this. It would be given in the data booklet, but since you wouldn't be given the data booklet anymore, so it would be stated in the question itself. But it's better to just remember that it's just 8.31. Always, I mean, better to remember that. Okay.
Sir,
Yes.
will we not be given the data booklet?
Now the thing is, they will actually whatever values you need, they would be given in the exam. Like,
okay, thank God. Because I thought that we could memorize our energetic things.
No, like I'll just give you an idea. Like in physics, you had like if I pick any paper out for physics, just a second. So I'll just show you how it's probably going to be done now. That in physics, you have all these constants given, right? I mean, they're part of the paper. Like in chemistry, you had a separate data booklet, but now they're probably going to print it and it would be made part of the paper. There's probably a specimen paper as well for chemistry. Just a second. Just one second. Log past papers 2022. So most values would be like even they've actually printed the periodic table. I mean, inside it, they are not giving it separately now. So whatever you need would be part of the question. So I'll just not this, trying to figure out. So for example, this is no, not this. So this is all inorganic. Just a second. No, this is not the kind of paper. It's just wanted to look at the energetics question. Just a second. This one, for example. You haven't done this, but this is the idea I'm giving. So whatever values you need, you'll be given a table inside. It will be quoted as part of the question. Okay, Hania, is this clear?
Yes, sir. Thank you.
Okay. So just remember this, like I mean, most of the papers that you'll practice for the exams, they would not be like this. Like whatever past papers you solve, because I mean, there's only one specimen paper available at the moment. So whatever past paper practice you do, keep this in mind, that at present, whatever you practice, you'll be working with a data booklet. But in your exam, the data booklet would be part of the question. Whatever values you need, the table would be quoted next to the question. So coming back to this question. So this one, PV equal nRT. Now it's a simple equation. We've combined all the relationships together. Now all you have to do is just plug in the values, and there would be one value that you would be looking for. Maybe you're looking for pressure. So the volume and the moles and the temperature of the gas would be given, so you can find pressure. Or maybe the pressure and the volume and the temperature are given, and you can find the number of moles. So if any one value is missing, you'll be able to figure this out. But you have to be very careful about one thing, and that one thing is the units. You have to be really careful about the units. Remember this, pressure is going to be taken in pascals. So if they give pressure in kilopascals, convert that or multiply it by 1000. So I'm going to write those conversions. So 1 kilopascals kPa is basically equal to 1000 pascals. So I think it's pretty obvious. So if they give you 100,000 kilopascals, just make sure you convert it into pascals. Similarly, pressure is also taken in atmosphere. So 1 atm is equal to 101,325 pascals. So make sure pressure is taken always in pascals. I mean, your equation over here, I mean, this equation will not work. I mean, the gas constant is for pressure taken in pascals. Similarly, the volume must always be in meter cube. It should always be in meter cube. Not in dm cube, not in cm cube. So if they give you volume in cm cube or meter cube or dm cube, you have to convert. Otherwise, you're not going to use this equation if it's in cm cube. So the conversion is cm cube to dm cube and dm cube to meter cube. So our conversion is you divide by 1000. And this one as well, you divide by 1000. And if you want to go back, I mean, sometimes they're looking for answers in cm cube. So even if you find it in meter cube, you would have to convert back. So you'll multiply it by 1000. So anyways, hopefully everyone knows this conversion, that how to convert things into meter cube. So directly from cm cube to meter cube, that's divided by 10 power minus 6. Or sorry, 10 power 6. 2 times by 1000. 10 power 3 divided by 10 power 3. So that would become 10 power 6. You want to go back, you multiply twice by 1000. So remember this conversion, and the value that has to be put in your calculator would always be in meter cube. Now, N over here is moles, which is fairly obvious. And you've got a number of formulas for calculating moles. So N is moles. Now, the formulas for moles that you can use are moles equal to mass divided by AR or MR. I'm going to write down all those formulas. So if the mass of the gas is given, you can find moles. So then you have another moles formula, which is moles is equal to, I mean, you can't use, I mean, concentration times volume can be used, but it's usually not for gases. It's for solutions. Although you can apply this formula for gases as well, but for gases, you don't use that. So this is usually not for gases. So you're never going to find moles of a gas using concentration times volume. That generally applies to a solution, but it is applicable to a gas as well, but mostly not used in this case. Then you had another formula, which is moles is equal to volume of gas divided by 24 dm cube. Hopefully everyone knows this. Now, specifically about this formula, that moles of gas is volume of gas divided by 24 dm cube. Never use this moles formula with PV is equal to nRT, because remember this statement is only true at RTP, room temperature and pressure. So a gas expands and compresses it if you increase temperature, if you decrease volume. So a gas is compressible. So the volume of gas is 24 dm cube, 1 mole of gas is 24 dm cube, but it's only true at RTP. Remember, when you're using PV is equal to nRT, you're basically not at RTP. The pressure is something else, the volume is something else, the temperature of a gas is something else. So this statement over here is only going to be true at RTP. What I'm going to do is, Okay, let me finish this, but remember this. They never use this formula. Be very careful in A-levels, this 24 dm cube thing, it only works at RTP. So you have to be very careful. Are you at RTP or not? And what is RTP? RTP is 25 degrees centigrade and 1 atm pressure. So that is what RTP stands for. Otherwise, it's not going to be true. And what's the last formula for moles that you usually use? I mean, if you know the number of particles of a gas, you divide it by the Avogadro's constant, which is 6.02 times 10 raised to the power 23. So that's another moles formula that you're going to use. Anyways, the only moles formulas that are going to work with PVZU NRT are either the mass of the gas is given, and you can find the moles of gas. Concentration times volume, usually that's not used for gases. This one, never going to be used with PVZU NRT because this one is only true at RTP. And you're not at RTP. The temperature could be anything. And the last one could be used. And the very last thing is temperature. The temperature has to be in Kelvins always. Be very careful with this. It's always going to be in Kelvins. So if it's given in centigrade, make sure you add 273 to it so that the temperature changes into Kelvins. So make sure, I'm just going to go over this again. Make sure when you use PVZU NRT, you know the ideal gas equation, you know the relationship between pressure, volume, temperature, and moles. Pressure must always be in pascals. So whatever pressure you're given, convert that into pascals. Volume must always be in meter cube. Moles, you can find moles using this, but don't use this formula ever. Temperature, it's going to be in Kelvins. So what I'm going to do is, the first simple question I'm going to do is, let's say, prove that, so try and prove that 1 mole of gas occupies, so let's prove that 1 mole of gas occupies 24 dm cube at RTP. So let's try and prove that. So I need to figure out the volume. So I'm going to try and figure out 1 mole of gas. Would it occupy 24 dm cube at RTP or not? So the pressure is going to be in pascals. It's going to be 1 atmosphere. So it's going to be 101,325 pascals. The volume I'm trying to figure out, what volume would be occupied? So this is P into V is equal to nRT. N is 1 mole into R is 8.31. And the temperature has to be in Kelvin. So what is 25 degrees centigrade in Kelvins? You add 273 to it. So if you do that, you're going to get 298 Kelvins. So I'm going to try and figure out, do I get the same volume or not? So what I'm going to do is I'm going to take 101,325 to the other side. So I'm going to take that to the other side, and I'm going to try and figure out the volume. So all I have to do is it's 8.31 into 298. So let's try and solve this. 8.31 star 298, and the whole thing divides by what? 101,325. So I'm getting something like 0.0244. So I'm getting 0.0. Let's round it to 2 significant figures at the moment. So 0.0244. And my answer, remember, if I'm using PVZU NRT, my volume is going to come out to be in meter cube. So how do I convert meter cube to dm cube? I multiply it by 1,000. So if I multiply this thing by 1,000, so that I can convert it into cm cube, it's going to become, this would become 24.4 dm cube, which is kind of close enough. So every time you studied in O levels that 1 mole of gas occupies 24 dm cube, that was just accurate up till 2 significant figures. So you got an even more accurate value. So we figured out that we have kind of proven that 1 mole of gas occupies 24 dm cube at RTP. Is this clear? Is that clear? Hania, is this clear?
Yes, sir.
So the idea is you can use this equation. Just remember, from now on, 1 mole of gas occupies 24 dm cube is not, it's only true at a very specific point. That's it. Otherwise, whenever you're trying to find the moles of gas, use this formula. This is the ideal gas equation. Yes, exactly. This is only for gases. Okay, and it is for ideal gases. It's not going to work for solids or liquids. So इसीलिए I mean, this equation is going to be true at any gas behaves as an ideal gas at high temperatures and low pressures, because any substance would probably behave as a gas at high temperatures and low pressures. So that's your equation. Most of the questions are going to be very simple. The only mistake that people are going to make is with the units. Be very careful with the units. Pascals, they should be in meter cube. Make sure you do the conversion correctly. Temperature should always be in kelvins, and moles, never use this formula, but make sure you're able to correctly calculate moles. Out of the 4 variables, 3 would be given, so you'll be able to figure out the 4th one. P, V, and N would be given, so you can figure out T. So most of the questions are going to be very simple and straightforward. Just don't make mistakes using the units or you doing the calculations on your calculator. Okay? So we're going to do some past paper questions in the next class then. Okay? Ye clear hai saro ko?
Sir, is this topic finished?
Almost. We still have, I mean, it's going to take one more class and then we'll do past papers. Okay? Probably in the next class. We still have to do a few graphs and we have to do non-ideal behavior.
All right, Allah Hafiz.
Okay, take care, Allah Hafiz.
Sir, can you send these notes on WhatsApp?
Okay, 1 second. What I can do is I can share the board link. ये मैं group में share कर रहा हूँ, ठीक है? You'll have the board and it's being shared on WhatsApp, ठीक है? So ठीक है, okay everyone. Take care, Allah Hafiz.
Allah Hafiz.